Alright, we're going to continue with section 15.2 in this video. First, before I forget, in my last video where I was going over the type of regions we learned how to integrate over, I neglected to mention probably one of the most important sections, which was our change of variables sections, and that includes like cylindrical coordinates, spherical coordinates, all of that stuff. So if you want to go back and add, say for instance, something like this to your pictures. So let's say we had some region that looked like this. You can make, if we had something like this, for instance, we learned how to integrate over regions like that as well. So that was change of variables. So in that I would include spherical coordinates, cylindrical coordinates, all that good stuff. So you can add that back to that list of pictures if you want to. Well, now carrying on where we left off in the last lecture, we talked about how to do a line integral of a scalar function. Now let's talk about how to do a line integral of a vector function. And you have to make sure, again, you pay close attention in your problem. Which one are you integrating? Are you integrating a scalar function or a vector function? So if, or vector field, if a continuous vector field F so now this is a vector function, is defined on an oriented curve, smooth curve. Sorry, oriented smooth curve. We need it to be a smooth curve. Smooth curve. And I've been orienting my curves, putting arrows on all of them. But you really only need an orientation on your curve if you're integrating a vector field. So you don't need it to be an oriented curve for a scalar function. But that's not, for the most part, we'll know our orientation for our curve. Smooth curve given by R of t equals x of t, comma y of t, comma z of t. Where t varies between a and b. Then the line integral of the vector field F over C is, so notationally the way we write this is the integral over C of the vector field F dotted with D in the vector function R. The way we evaluate is just the integral from A to B, that we take our vector field F and we take and substitute in the parametric equation x of t, y of t, z of t. So shorthand notation for that is we put R of t into here because F actually takes x, y's, and z's. So for the x, we're going to put in this function, y will put in that function, z will put in that function. And then we're going to dot this vector with the vector r prime of t. And now when we take this dot product, we'll just have some scalar function in here. It's going to be a function of t. And then we'll integrate that with respect to t. And this is where C is traversed exactly once. as t varies from A to B. And then you may see this written other ways. So let's look at another way we can write the same thing. So given the vector field f of x, y, z equals the vector whose first component is m of x, y, z, second component is n of x, y, z, and the third component is p of x, y, z. We may also use the notation, the integral, the integral, line integral over c of f dot dr equals the integral over c of m dx plus n dy plus p dz. So a lot of problems, they'll be written in this form. So you have to know that when you're doing this, you're just doing that exact same thing, or meaning you're doing that exact same thing that's right there. So we'll look at some problems this way and that way there. All right, so lastly, let's talk about how to compute work. And then after that, we'll do some examples. All right, so for work, I'm going to let's go to the next page actually. So let the vector field F be a force that moves an object along a curve C where our curve C has to be oriented in the direction of travel of the object. So oriented in the direction of travel of the object. Then the work W done on the object by the force F is W equals the line integral over C of F dot dr. So we'll use line integrals of vector functions in applied problems to find work. All right, so now let's look at an example. So we're going to start with number 10 in your textbook. So we are on page 1014 of your textbook. So page 1014, number 10. In exercises 1 through 10, evaluate the line integral. and they don't specify for us whether we have a scalar function or a vector function. So we have to be able to decipher the problem and figure out which of the two we have. All right, so, and some problems are going to be set up for us, some we'll have to set up ourselves. So this one, they tell us we are doing the line integral over c of 3x minus 2y plus z ds. So the ds right there is a clue to us, is that tells us we're doing a line integral of a scalar function, where c is as shown in figure 15.15. All right, so I'm not going to sketch the figure because you all have your textbook to look at. So now from our approach for line integrals of scalar functions and for our approach to line integrals of vector functions, we know we have to have a parameterization of our curve. So some problems will give us a parameterization. Sometimes we'll have to figure it out ourselves, but we learned how to parameterize curves earlier in the semester. So in this problem, we have to figure out how to parameterize this curve ourselves. And then from there, we can go through and find the line integral. So the curve that they drew for us has two parts to it. So it's a piecewise smooth curve. So we'll call one of the parts C1, and we'll say it's the line segment from, now they don't explicitly say, but we can see that the line segment goes out to 3 and comes up to, and lands on the circle of radius 1 centered at the origin in the YZ plane. So the line segment, and they also give us a direction to travel for it. So it's the line segment from what we'll call P naught, which is x equals 3, y equals 1, to the point, call it P1, which is 0, 1, and I should have 3 coordinates on here, so I should have 3, 1, 0 actually. So you cannot fix that. Not really. All right, so let's just do this. From P naught, which is 3, 1, 0, to P1, which is y is 1, then x is 0 and z is 0. So 0, 1, 0. So now how do we parameterize a line segment? So we learned this earlier in the semester. So this would be r of t equals 1 minus t times whatever your starting point is, plus t times whatever your ending point is. And remember that t, for that parameterization of the line segment, t goes from 0 to 1. So for us, that is r of t equals 1 minus t. So the point where we start is P naught 3, 1, 0. So 3, 1, 0 plus t times the point where we end is 0, 1, 0. All right, and then from that we can pull out our parametric equations from that. So we get x equals 1 minus t times 3 plus t times 0. So you should get 3 times 1 minus t. Y equals 1 minus t times 1 plus t. So we get 1 minus t and then plus t. So we just get y equals 1. And then for our z, we end up with 1 minus t times 0 plus t times 0. So our t is 0. Z is 0, and t varies from 0 to 1. So we parameterize the line segment, and now there's a quarter circle in that picture as well, so we need to parameterize that. So we'll call that C2. So usually you won't have two separate curves to parameterize. The fact that we have two separate curves means we're going to have to do two separate line integrals and add them. Normally you'll just have one. So the quarter circle and the YZ plane, starting at So we're starting at 0, 1, 0. And ending at, and the start and end come from the arrows that they give us. Ending at 0, 0, 1. My line, yes, 0, 0, 1. So now what we'll do is we'll parameterize this, and in parameterizing a circle in the YZ plane, we normally would use sines and cosines. In the XY plane, we would as well. So we're going to use sine and cosine to parameterize this quarter circle that we have. So since we're stuck in the YZ plane, we know X is always 0. So X equals 0. And then convention is that we'll take the letter that's closer to the end of the alphabet. We'll make that sign. When we choose sine and cosine for our Y and Z, so the radius of the circle is 1. So Y would be equal to cosine T. And also we want to make sure we're going in the counterclockwise direction as this circle is going. So you have to be careful about switching your sine and your cosine when you have an orientation. Make sure your orientation is correct. And then Z equals sine of T. And then for our bounds for T, if we want to get a quarter circle, we would have T going from 0 to pi over 2. And you can always just briefly check to make sure that when T equals 0, we're at our starting point, and when T equals pi over 2, that we're at our ending point for whatever it is that you're parameterizing. And now we're ready to go ahead and set up our integral, and they told us to integrate, they told us to do the line integral over C of 3x minus 2y plus z. Yes, plus z ds. And for us, we had to split C up into two. We had to split up C into two separate curves. So this is going to be the line integral over C1 of 3x minus 2y plus z ds. I actually put an S1 there, but that's not a big deal. And then plus the line integral over C2 of 3x minus 2y plus z ds. So we need to set these two integrals up. So now at this point, you want to go back and look at how do we do a line integral of a scalar function over some curve C, and see how do we substitute everything in there and what all we need to find. All right, so I'm going to write this down, acting under the assumption you are looking back at the notes so you can see how we put everything in there. Otherwise, it's going to take us a lot longer to put it together, and I want to make sure we can get to some more examples. So that we have on the previous page is equal to, so C1, our T values vary from 0 to 1. And then we take the scalar function that they gave us and we plug in the parameterization of the curve C1 into the scalar function. So we had 3x, so 3, and then x for us for the line segment was 3 times 1 minus t. So 3 times, let's do this, 3 times 1 minus t. And then next we have minus 2y, and y was 1, so minus 2 times 1. And then plus z, and z was 0. So plus 0. And then now that we put our bounds in there, it's not ds anymore. Back here it's dt. But I forgot about something entirely. We still have to do the magnitude of r prime of t. So that's what I forgot. So now we need the square root of dx dt squared plus dy dt squared plus dz dt squared. So the derivative of x with respect to t, and we can see what x is right there, y is right there, and z is right there. So the derivative of x with respect to t is just going to be -3, and then we square that and we get 9. The derivative of y with respect to t is equal to 0, and we square that and we get 0, and the derivative of z with respect to t is 0. We square that and we get 0. So plus 0 and dt, and we don't want to forget about our other integral. So plus now over c2. Our bounds for c2 were something 0 to pi over 2. And then we had 3 times our parameterization for c2. X was 0, so 3 times 0 minus 2 times y was cosine of t. And then plus z, which was sine of t. And then times the magnitude of r prime of t. So for us, that is the derivative of 0 with respect to t, which is 0 squared, and then the derivative of cosine with respect to t, which gives us negative sine t, and then we square that, which gives us sine squared t, and then plus the derivative of sine of t, which is cosine t, and we square that and we get cosine squared t. So we just end up with the square root of sine squared t plus cosine squared t. So we just end up with the square root of 1 dt. And now we're back in calculus 1 after we simplify this. So because we're just integrating this, I mean, this is just a constant that comes out. Of course, that 1 simplifies. And you simplify this and you integrate everything with respect to t, put your bounds in, and add those 2 integrals. All right, so we'll stop this video here, and then we'll do an example of integrating, doing a line integral over integrating a vector function, over curve C.